So far, we have been using Python for coding the algorithms that we are developing in this course. For speed up, let's use a compiled language. Let's code here now an example of the Euler method in Fortran90. Let's first open the program. In Fortran, a program starts with the statement program. So let's call this program Euler. And it must also be finished with the statement end program. There you go, program and end program. That's different than in Python, where the indentation gives you the end of a statement. That's not the case in Fortran, where the indentation is there to help you, but it does not affect the program. So just like in the Python programming, the core of this program is the update on the velocities and the positions. So these are the lines that we want to get to in the end, right? We want to update position and velocity, and we want to advance time. Everything that we build in the program is going to be leading to these lines. So let's find out exactly what we need to do. We know that the x dt is just the velocity, and we need to loop through all the particles in the program to find the accelerations. Here we need a loop. So for every particle k, we need to loop through all of the particles j and define the acceleration. So this RR square here is the separation. Let's define that too. First, let's do the loop. We need to loop for the particles. So in Fortran, this is how we do the equivalent to the for loop in Python. It's a do loop. You give the index and you give the lower limit and the upper limit. And part here would be the number of particles there are in the simulation. And again, because the indentation exists in your mind, but does not do anything in the program, you need to close the do loop with an and do. Let's also use an if statement. So we should exclude the particles that have equal index. So exclude j equal k from the calculation. And again, close the if loop. You see that the not equal sign is actually slash equal. Usually the not equal sign in most languages is exclamation mark and equal, but the exclamation mark in Fortran90 is the comment. The exclamation mark is taken, so another operator is used for the not equal, that's the slash equal. So what is needed now is to calculate the scalar separation, the RR squared. Let's loop them for the directions. And let's not forget to comment the code so we know what we're doing. And that is already most of the program. That's the core of the program. Now we need to define the initial conditions and do the looping time. So let's start that. Let's first do the looping time. Let's do here, the loop is going from I to t. Now let's put everything here in the indentation. Start the VDT with the 0. Now, one thing that I like in Fortran is that you can label the loops. You can call this here first the time loop, and then when you finish it, it gives you here the name of the loop. Again, you don't need to label the loops, but it helps you, especially in a big code, it helps you know which loop is it that you're ending. Now let's define the quantities that we need here to start the loop. We need to define in t. Let's define also Tmax. Tmax would be the number of orbits that we want to calculate in the simulation times the orbital period. The orbital period is 2 pi over the mean motion. We need to define the number of orbits. Let's say that we want 10 orbits. We need to define the timestamp. Let's say that we want to have it as 10 to the minus 3. You need to define pi and the mean motion. For the mean motion, let's use the semi-major axis being equal to 1. The mass of the star being equal to 1. Now for the mass, let's use Q, the mass fraction, and give them the mass of the planet be equal to Q, and the mass of the star be equal to 1 minus Q. The mean motion then is equal to G times the mass. Based on these definitions, we can set the initial condition. Set the initial condition for the star. The position in X is minus Q. The position of the planet is 1 minus Q. Also define the circular velocity, which is the mean motion times the semi-major axis. This would be the position of the star, the velocity of the star, minus Q times the circular velocity, and the velocity of the planet. Now we need to declare the variables. That's a major difference between scripting languages and compiled languages. The variables must be declared. So let's see how we do that. Every single variable that is defined, every single variable that is used here, you must declare them. So let's start here. I have here Q, SMA, these are real variables. Mass here is an array. So real, dimension, and par. Now, par is a parameter. That's a little bit different than just an integer. It's an integer parameter. Let's declare as 2. It's because it's an integer that is being used in the declaration of another parameter. Let's see other quantities. Mu, g Newton, set g Newton equal 1. Declare me motion. Now x and v are two-dimensional arrays. The first dimension is which particle is the particle index, and the second one is the dimension. Let's define also ndim as a parameter, the number of dimensions. So there are 3 dimensions. We're going to need also dx dt and dv dt. The circ now, nt here is an integer, is specifically declared as an integer. Now the counters are also integers. So it is an integer, k and j are integers, r are 2, and we're using these quantities here, I star, I planet, ixp, iyp. All of them should be defined that they are integers also. And we can give their value in the declaration. So we're going to say I star is equal to 1 and I planet is equal to 2. And same thing for the ixp equal 1, iyp is equal to 2, and yzp is equal to 3. Now that's another difference here. In Python, the arrays are started as 0. In Fortran, they're started at 1. Now that's the difference between C and Fortran. Python is C-based, and in C, the arrays start from 0. In Fortran, we do the human counting. When you count things, you start from 1. You have 3 apples, you're going to count 1, 2, 3, not 0, 1, 2. But in C, it's counted as machines count. Machine counts in binary, so 0 and 1. So it would start from 0. It's not that one is better than the other, just different definitions. Now the time, we need to give time. Time is a real. And should start the time also as 0. Now the last variable we need to declare is pi. Pi is not defined. It's a real parameter. We need to declare and give its value. So we're ready now to compile. For that, let's go to the shell and use gfortran, which is the GNU Fortran compiler. We call the code Euler.f90. To compile like this is going to give you an A out, which is an executable. Now we are not printing anything. There is no output here in the code. Let's put some output. Let's make the code print out some variables. So this is the modules here. We get IT, which is a counter, and when the division by IT by this number IT0 is equal to 0, then it's going to print some output. Let's define now this IT0. That's the frequency of output. Give it every 100 time steps. There we go. The code's printing. Now, instead of AO, you can actually specify the name of the executable. Let's call it EulerX. Now let's time the code. CPU time is a built-in function. We can start that, and let's define start and finish variables and print the time in the end of the code. So let's time the code now, see how long it takes. It took about 10 to the minus 2 seconds. While fast, it's not as fast as it can get. So let's use optimization. There are several places in the code where we are using exponentiations, when we're using divisions and loops. You can use an optimization flag so that the code saves time during compilation. Now you see it decreases the time by a factor of 2, just due to this optimization. Now there's another thing that is going on. We are making the code print, and we know the printing is slow. So let's see here, what if we're printing every time step, right? Change here IT0 to 1. Now the code took 0.43 seconds, so almost half a second. It's a lot slower. Printing is slow. See here, if you do IT, limit the frequency of output to every 1,000, now the code took 4 times 10 to the minus 3 seconds. What if we remove printing altogether? How fast will the code be? 4 microseconds. So printing, at least printing to the standard output, is very slow. Now lastly, let's encapsulate the initial condition. That's going to show us how to use functions. You saw the call here calls a subroutine. In this case here, CPU time is a built-in. We can actually call a subroutine initial condition to set the initial conditions for us. Let's put it here, and all of this block here, say given the mean motion and the masses, let's encapsulate that into a call for initial conditions. And let's see, we wanted the initial condition to give us the masses, the positions, and the velocities. So all these blocks are going to go in the initial condition. The way that we do that is after, in the end of the program, outside of the program, we start a subroutine. Let's call that initial condition. Same name that we gave. Then end it again with an end subroutine. And that's what we want the subroutine to do, to give us mass, mu, mean motion, x, viscert, and velocity. So we need to input these quantities. So you need q, mass, x, v, I planet, I star. So these are the variables that are needed. We need to pass these variables then in the call. Also need G Newton, and we need to declare the variables here again. Now, one thing that is not necessary, but I like to do, is to specify which variables are input and which variables are output. Now, in Python, you would call it in a different way. You would give the output, every function would have a return, and these are the variables that you're going to put on the left-hand side and an equal sign for the function. And it's only the input variables again in the call of the function, right? In Fortran, it's different. As you see, you put everything on the right-hand side, and you do not need to specify which ones are input and which ones are output, but I find a good practice. So let's say here, the variables that are being used are q and par and dim. Now, if a variable is given with an intent in, a subroutine cannot change them. And if a variable is given as intent out, its value must be set within the subroutine. So these are the variables that are going to be output. It's x, v, the mass, and the mean motion. There's also the variable mu, which is used, and viscert is also used in the subroutine. Right. There's one less variable missing, the SMA here, the sum major axis. So let's put that in here. Compile again. And there you go. So that is the Euler method in Fortran.